Have you ever wondered how computers can recognize faces, objects, or even emotions in images? Well, the secret behind this incredible ability lies in a fascinating field called neural networks, and specifically, their application to image recognition. In this video, we'll take you on a journey to explore the inner workings of neural networks and how they're revolutionizing the way computers see and interpret images. Pixel brightness is a fundamental concept in digital imaging, representing the luminance of a single pixel in an image. It's typically measured on a scale ranging from black to white. In the image, the scale ranges from negative 1.0 to positive 1.0. A value of negative 1.0 corresponds to pure black, while positive 1.0 represents pure white. The value 0.0 denotes a neutral gray, exactly halfway between black and white. The number of distinct brightness levels that can be represented depends on the bit depth of the image. For example, an 8-bit image can have 256 different brightness levels, from 0 to 255, while a 16-bit image can have 61,656 different brightness levels, from 0 to 61,555, 65,536 levels. On the left side, we have a representation of a neural network node. It receives input from 4 sources, visualized as a 2 by 2 grid. Each square in the grid represents a pixel or a feature value. These inputs are connected to the node through arrows. Each arrow has a number associated with it, which is the weight of the connection. In this case, all weights are 1.0, but in a real neural network, these weights can vary. The weights determine the strength or importance of each input. The node itself has a value, which is calculated based on the inputs and their weights. The calculation is shown on the right side of the image. First, each input value is multiplied by its corresponding weight. Then, these products are added together. Finally, a bias term is added to the sum. The bias allows the node to activate even when all inputs are 0. The result of this calculation is the node's output, which is then passed on to other nodes in the network. This process of weighted summation and bias addition is a fundamental operation in neural networks. It allows the network to learn complex patterns and relationships in data. The weights and biases are adjusted during the training process, allowing the network to improve its accuracy over time. The sigmoid function is a mathematical function that takes any input value and squashes it into a range between 0 and 1. It's like a smooth S-shaped curve. Imagine a neuron in a neural network receiving a signal. This signal can be any number, positive or negative. The neuron needs to decide whether to fire, activate or not, based on this signal. Here's where the sigmoid function comes in. It takes the input signal and transforms it into a value between 0 and 1. This value represents the probability of the neuron firing. If the input signal is very negative, the sigmoid function outputs a value close to 0, meaning the neuron is unlikely to fire. If the input signal is very positive, the output is close to 1, meaning the neuron is likely to fire. The sigmoid function is particularly useful in situations where we need to model probabilities or make decisions based on continuous input values. For example, in image recognition, the sigmoid function can be used to determine the probability of an image belonging to a certain category. The sigmoid function is just one of many activation functions used in neural networks. Each activation function has its own unique properties and is suitable for different types of tasks. An image, as a neural network perceives it, is fundamentally a grid of numerical values. Each value corresponds to the color or brightness of a single pixel, the smallest unit of an image. For a convolutional neural network, CNN, this numerical representation is crucial. CNNs are specifically designed to process image data by employing a technique called convolution. This involves sliding small, filter matrices across the pixel grid, extracting features like edges, textures, and shapes. By learning these features at various levels of abstraction, CNNs can effectively understand and classify images, recognizing complex patterns that would be difficult for traditional algorithms to detect. Imagine you have a large image, and you want to extract specific features from it, like edges or corners. You can use a technique called convolution, which is like sliding a small magnifying glass over the image. This magnifying glass is called a filter or kernel, and it's a small matrix of numbers. As the filter slides over the image, it multiplies its numbers with the corresponding pixel values in the image. These products are then added up to produce a single output value. This output value represents the strength of the feature that the filter is designed to detect in that specific region of the image. The filter continues sliding across the entire image, producing an output value for each position. These output values form a new matrix, called a feature map, which highlights the areas where the specific feature is present in the image. This process is repeated with different filters, each designed to detect different features. The resulting feature maps are then combined to create a more comprehensive representation of the image, which can be used for tasks like image recognition or object detection. Convolution is a powerful technique because it allows the network to learn and extract relevant features from the image, regardless of their position. This makes it particularly effective for tasks where the location of the feature is not important, such as identifying objects in an image, regardless of where they are located.